Hi there, Physics 131. This is the pre-class video going over some of the reading from class 24, or at least showing it to you. So it's all about static equilibrium. And it starts with this, again, observational experiment in which you have a meter stick and you're pulling it with 3 different spring scales. And I think it's actually easiest to see it if you watch this video, what the heck is going on. There's three scales attached to this thing. They pull them until the whole thing kind of comes into an equilibrium. I don't know what they're talking about exactly there, but basic idea is that there's a 3 Newton down force, a 9 Newton down force, and there's an upward force of 13 Newtons, and there's also, I guess, the weight of the meter stick itself, which is 1 Newton. So what's basically going on is there's 3 equations. The first 2 are the sum of all the forces in the x direction equals 0. And that's actually true because they're all y forces in that particular example up there. The sum of all the forces in the y direction also equals 0. So the upward forces have to balance the downward forces. We kind of know these from before because it's not accelerating. And now there's a third condition, which is that the rotational torque is equal to 0. So you sum up all the torques. So there's going to be some clockwise torques around some axis and some counterclockwise torques, and they're going to balance each other out. So it shows you some examples of that. There's a nice little hint here which says that, remember, we have the freedom to choose whatever axis of rotation we want. So this is a little bit like defining the coordinate system. It's kind of important where you choose the rotation axis, but in static equilibrium, it's not rotating about any axis. So the torques have to balance around any axis you choose. But some axes will help you solve the problem you're trying to solve, and some axis choices will not. So definitely read through section 8.3. Section 8.4 is called center of mass. This is mostly talking about gravitational torque, but it talks a bit about, where is the jumper's center of mass? There's apparently, this is a high jump technique. You can bend your body so that the center of mass passes under the bar. So basically, if you have sort of a C shape, if I put my hand in a C shape like this, then the center of mass can be sort of not part of that. It'll be in the center of all the mass. And so you can imagine that going under while you still clear your body over the bar. That's a technique in the Olympics. They talk a little bit about getting out of a chair without using your hands. So your base of support normally has to be under your center of mass in order to have stability. So how do you calculate center of mass? Well, certainly if there's 2 objects and one's heavier and one's lighter, the center of mass will be closer to the heavier apple here than the lighter apple. So that's the sort of conceptual idea for it. There is an actual equation somewhere. Here it is. It's the x position of the center of mass is, and there's a lot of things here, it's the sum of all the masses of the particles times their positions divided by the masses of all the particles, the total mass. So when you calculate things in reality, like here's a good example. Where's the center of mass of the 2 people sitting on a seesaw? So there's actually 3 objects here, the 2 people and the seesaw itself. So you add m1 times x1. So you have to define a coordinate system once again where your origin is, and once you do that, every mass will have its own position. So we actually define the origin to be at the position of the 60 kilogram mass. So you do 60 times 0. The center of the seesaw is now going to be at a distance of 1.5 meters, because it's a 3 meter long seesaw. 1.5 meters will be the center of mass of that times the 20, and then plus the 20 kilogram mass on the right, which is 3 meters away. And you divide it by the total mass and get the x center of mass. So have a look through that as well. Again, I encourage you to do all the reading, but this is a quick overview for today's class. See you in class. Bye for now.